are the photovoltaic system design team. I'm Tanisha.
I'm David.
I'm Eddie.
So just a brief background into our project. As you all know, the awareness for sustainable energy and solar energy has been increasing over the past years. And a lot of universities have been doing a lot of developments on studying solar panels and solar technology. But unfortunately, University of Illinois has been a little bit behind in terms of actual implementations. So that brings us to the objective of our project, which is to design and develop a system, a solar panel for a university building to help decrease costs and, more importantly, to increase environmental awareness. This project has been repeated in past years. So in order to add value, we are choosing a more appropriate building for this year. In the past, there's MSCB that was done in the ARC, but this year we're doing a more appropriate building. And also we're identifying funding sources because of the expense of solar panels. We're trying to make this an actual feasible project so we can submit a proposal to the university.
I'll discuss the building analysis briefly. So the initial proposal was for us to investigate the MSCB, but in further review we decided that it was not one of the most appropriate buildings due to area constraints on the south roof. So we investigated the Seibel Center, the ARC, the new ECU building, which is currently being constructed, as well as the Speech and Hearing Science building. Ultimately, we decided on the Seibel Center due to its large south-facing roof area that is also sloped at an appropriate angle for our latitude, so there's a maximum light absorption. And it's also visible on the engineering campus, which helps promote green energy. As you can see here, this is an architectural drawing of the Seibel Center that we acquired courtesy of Beth Leitz at Facilities and Services. And zooming in closer on the next slide, you can see the very bottom of the south-facing roof, and there are distances and lengths that you can see there, as well as the far east side of the roof and the lengths there that were used to calculate. And these designs are courtesy of these architectural and engineering companies. And on the next slide, I've created a schematic that shows the slope of the roof, which ended up being 26.57 degrees. The length ended up being just under 98 meters, and the width was just over 18.5 meters. Using these lengths and widths, we were able to calculate a maximum possible roof area of just over 1,800 square meters. And as you can see on this Google image, this is the area of the Seibel Center roof, which we were planning on implementing the solar array.
So I'll be talking about the different solar technologies that we looked at for this project. So we looked at a few different technologies, silicon varieties, including monocrystalline silicon, polycrystalline, and amorphous, but also thin film varieties, including cambium telluride, which is being developed primarily by First Solar, an American company, and also copper indium gallium diselenide. So monocrystalline silicon is advantageous within the silicon varieties because it has fewer grain boundaries and is therefore more efficient. And also the electronics industry has a lot of experience with manufacturing this material because of its use in the electronics industry. Thin film solar panels have been developed primarily in the past 10 to 15 years in response to certain drawbacks with silicon. Silicon is a relatively poor absorber of light, and the panels made of silicon have to be very thick, hundreds of microns. Thin films have the promise of offering lower material costs because they're much thinner than the silicon panels. But the drawback of this is you get lower efficiencies. So this is the trade-off that researchers have been working with. So there were a few different criteria that we examined for choosing a technology. We defined our value as being the total cost of the panel, which includes the modules themselves as well as installation costs, which are very significant. And we divided that by the first year output as a means of comparing between the different options. We also wanted a warranty that was at least 25 years. This is a long-term project. And that specifies, that's a guarantee by the manufacturer that efficiencies won't drop by more than 20% over that period. And lastly, we wanted a technology that's been field tested for this period of time. As I mentioned, thin film technologies are newer, having been developed in the past 10 to 15 years, so we don't actually know how they hold up over a 25-year period. And this is actually a risk outlined by First Solar in their annual 10K report. You can read the excerpt here, that they don't know how cadmium telluride actually holds up over 25 years because it's a newer technology. So I doubt that First Solar is losing sleep over this, but it's a risk that should be considered. And these drawbacks led us to look within the silicon technologies, and we ended up choosing monocrystalline silicon because it offered the best value. So solar technologies are very dynamic. New research is being done and advances are being made very rapidly. So the question arose last time whether it would be better to wait 5 to 10 years for the technologies to improve and think about implementing down the road versus implementing today with current technologies. So because research is so dynamic and it's extremely difficult to forecast where efficiencies are going. But this here is a chart from First Solar's cadmium telluride, what they've done in the past few years from 2006. And if you look at that time period, you've had efficiency gains of roughly 0.5% a year. And we could compare that with monocrystalline silicon from Suntech, Chinese manufacturer. And this is looking from 2008. You can see where their best modules have been going and the efficiency gains that they've had over the past few years and where they're projected to go. So thin film technologies and silicon technologies are expected to improve in efficiencies over the next few years. It's not like one is rapidly outpacing the other in development work that's being done. So with an understanding that these technologies are all improving at comparable rates, and the understanding that projections about the future with this industry are widely inaccurate, very difficult to make due to the nature of the research, we decided that it would be best to make our evaluation with the information that we know today. And that let us confirm our choice of monocrystalline silicon.
So I'll talk a bit more about the calculations and the estimates that go into calculating the cost and all the savings. So instead of the 1,800 meters squared roof area, we reduced that by around 10% to account for maybe maintenance area or any gaps that we might have during installation. So we'll be using around 1,600 meters squared of the roof area. Also, you can estimate the energy from the sun hitting the earth to be at 1 kilowatt per meter squared, roughly. And the sunlight we get in Champaign, we get around 1.8 kilowatt-hour per watt year, which is equivalent to around 5 hours of full direct sunlight per day. And the figure on the right shows that Illinois is on the moderate range. And also, the current energy cost for Seibel is 8 cents per kilowatt-hour, and it was 7 cents last year, but it has risen up to 8 cents this year. And using those numbers, we can calculate how much we would save. So I took silicon panels from 3 different companies, and which are Trina Solar, and Suntech, which are Chinese companies, and also Sanyo. So you can see the efficiency is pretty much outlined the watts per meter squared, and they're all quite similar. With each respective companies having their monosilicon obviously slightly higher than the polycrystalline silicon. And this leads to a total power output of around 250 kilowatt system. And the installation cost is a big deal. So we can't really estimate the installation. We can't really say for sure what the installation cost would be, because the process would be going through the facilities and services. So we talked with Professor Rocket, and he said that $4 per watt would be a pretty reasonable amount. It could be as high as 5 or 6, but it could also be as low as like $2 per watt per kilo. Yeah. So all in all, it comes out to be around $1.5 million roughly, and with each panel saving around $30,000, $35,000 a year, and payback period of ranging from around 35, 36 years to all the way up to 46 for the sand deal. And however, with our funding strategy that Vijay will talk about later on, we might be able to get the university to pay only 20% of that total cost, which will lead to a shorter payback period. So within these, we recommend only the sand yield, but in reality we wouldn't have a choice because we would be submitting the proposal, and the FNS people would actually be doing the bids, and they would actually be the ones selecting. But we would recommend the sand yield because with the university payback period, there's a very little difference between each technology, and after the payback, you would gain more with the sand yield since it has the highest annual savings. And so we also took into the consideration that monocrystalline, we show some examples here, is that the polycrystalline, each individual grain would reflect a different contrast and color, so it wouldn't be really nice on the roof of the Seibel Center, and we've been told that aesthetics is a pretty big consideration, so it would narrow it down to monocrystalline silicon, which are uniform color, either blue or black. So also for mounting options, FNS stated that they are very strict on penetrative mountings, and they want to minimize any penetrations on the roof because that could cause leaks or worse collapse of the roof possibly. So there are options for non-penetrative mountings, and an example is shown in the picture where the Seibel roof actually has a very similar texture to this roof because it has like a vertical ridge kind of thing. So there's several ways to mount this. For example, like hook it on the top of the roof and have supports all the way down. But some considerations during mounting is that you need some amount of gap underneath to promote cooling, because solar panels have higher performance when it's cool. But also you don't want the wind going underneath and lifting up the panels, because panels are quite large and there could be a lot of load on the panels. So also you have to consider the wirings and other components such as like inverters, where you want to place them possibly underneath the roof, or you might wire them all the way down to the ground level. So these are some components that the installation people would have to take into consideration.
So we also looked into potential funding sources for this project. As I mentioned earlier, solar panels are very expensive, and in order for the university to actually install it, they would need us to find sources of funding. So some potential resources we looked into, first the Student Sustainability Committee. It's an organization/committee on campus, and they work to promote environmental awareness, and they fund projects. So they were a key resource. Illinois Clean Energy Foundation, as well as Illinois Department of Commerce and Economic Opportunity, both are geared towards improving sustainability within the state. So they were also considered, and then university alumni, corporate sponsors, U.S. Green Building Council, and then any kind of federal grants and tax breaks. But in order for facilities and services to actually take our proposal into account, they wanted us to come up with a funding strategy. So what I did was I went through and looked at previous estimates for what these funding sources gave for similar implementations on university buildings. So from that, we came up with that the Division of Commerce and Economic Opportunity would probably give about $500,000. They have an annual budget of about $21 million that they can spend in the state funding government projects. So that was one estimate. We also came up with a plan for the alumni to donate the modules. That way the alumni have a way of giving back to the university, and it was a way for us to reduce the cost as well. So about $500,000 for that. And then Clean Energy Foundation in the past has given about $350,000 for similar solar panel implementations within the state. So we had that estimate. And then Student Sustainability Committee, Morgan Johnston was one of the people we met up with. And she told us that they have about a budget of $1 million each year. And for something like a solar panel implementation, they would probably contribute about $300,000. So all of those add up to $1,650,000. Most of the solar panel purchases that we projected were going to be solar panel purchase and installation. Costs were going to be around $1.5 million, so that should cover most of it. If any more money is needed, then the College of Engineering promised to fund at least 20% of the cost. But ideally, if we can cover it with external sources, then the university payback period would be zero years.
So I'll talk about some of the next steps of our project. Now that we have everything in place, including potential funding sources, we can go ahead and submit a brief report to the Student Sustainability Committee and Morgan Johnson at Facilities and Services. Like I said, the funding must be in place prior to submittal so that they take our proposal seriously. And the report also must be submitted by a manager of facilities at the Seibel Center so that there's a non-student name associated with the project that Facilities and Services can be in contact with. After that, we will work with Facilities and Services to attain approval on certain details of the project. There are many considerations, like Put said, non-penetrative mounting, so there's a minimally invasive procedures on the building themselves. The issue with implementing a photovoltaic system on an existing building is the mounting because they don't want to structurally compromise the building. There are also other budgetary considerations. If the project is over certain budgetary levels, different bureaus must approve the project on campus, and different boards involving the chancellor and aesthetics, as Bud also mentioned, have to be taken into consideration and approved as well. After these things gain approval, Facilities and Services will send the project description to a variety of companies in a search for bidders. Once an adequate number of bidders are attained, Facilities and Services can go ahead and select the appropriate bidder. And this is also the issue that Pud was talking about earlier, where we cannot decide on which specific technology or mounting options or installation options that we would ideally want, because once Facilities and Services hands us over after the bidding process, the company that takes over will be in charge of all the that decision making. So after that top bidder is selected and they decide on the technology and implementation process, the project can begin. This was our initial project timeline, and we successfully completed everything that we set out to do, with the exception of meeting with Tom Abraham, who is no longer at the university. And that concludes our project, and thank you for our time.
Did you complete a similar cost analysis for thin film cells, comparable to what you did with the silicon cells, to see if they came out to be some sort of parity, perhaps?
Well, we stopped the consideration on thin films after we realized that they hadn't been field tested for a significant amount of time, so we didn't want to trust a technology that could potentially fail well short of a potential payback period. So we did not complete that cost analysis.
Okay, so that's sort of, so it would definitely be far beyond, or, you know, it could easily fail before then, I guess.
Yeah, we just don't know. It hasn't been field tested to that extent.
Yeah, maybe not easily, but it could.
Did you guys factor in like the installation costs, like after the lifetime, or are you just planning on keeping it up there after 25 years? Or?
We only looked at installation.
All right, thank you very much.